Junita Mukherjee once again in SS Public School, giving you some notes about a new chapter, which is the ray optics and optical instrument. So in this particular chapter, I will not be going to tell you about the topics which we have already learned in 10th standard. You just revise the topics which are given already in the book, and it is from this 10th standard. We will discuss some new topics which are not being told to you in 10th standard. So first topic is principle of reversibility of light. Principle of reversibility of the light means it's going from one point to the another point in that same manner. It is reversing back in the same manner. So in the point it is going one interface to the another interface, it is coming from that particular opposite interface, from that opposite, so let it be sin R and sin I and sin R. It is going from sin I to sin R, and it is returning back from sin R to sin R itself. That is what we call the reversibility. Let us see what is there. When a light ray, after suffering a number of reflections and refractions, has its path reversed, final path reversed, its travel back its entire initial path, it is called principle of reversibility of the light. In the figure, OA is an incident ray in the medium 1 and BA is the refractive ray in the medium 2. By Snell's law, the refractive index of the medium 2 relative to the medium 1 is given by 1 mu 2 is equals to sin I upon sin R, first equation, where I and R are the angle of incidence and refraction respectively. So it is coming from this particular position I to R itself, and it is going back again in the same direction. There is a mirror here placed here, and it is going out in the same direction in that particular area itself. This will be sin I again, and this will be sin R again. Okay, so how it is? Suppose the ray AB is reflected back by a plane mirror, or now AB will be incident ray and OA is the refracted ray. So AB will be incident ray here, and this will be refracted ray here. So corresponding R angle of incidence, and I is the angle of refraction. Again by Snell's law, medium number 2 means the refractive index of the material of the medium 1 relative to the medium 2 is being given by 2 mu 1 sin R upon sin R, second equation. Now multiplying equation number 1 and 2, if you multiply sin I upon sin R into sin R upon sin I, we can cancel the whole value and we will get 1 here. So it will be equal to 1 mu 2, that will be equal to 1 by 2 mu 1. 2 mu 1. So this is how the refractive index of the medium 2 relative to the medium 1 is equal to the reciprocal of the refractive index of the medium 1 related to the medium 2 itself. So looking forward for yet another topic in which I will tell you the refraction of light through a rectangular glass slab, and expression for lateral displacement. So these two I will tell you in this particular video only. Let's see these two things. So let's see this thing, expression for lateral displacement. In this lateral displacement, first I will tell you what is the lateral displacement here. When we are taking this particular ray into action from a glass slab, this is air, glass and air. This is the two pins we have inserted here in this particular incident ray, and this is normal here. We have drawn again one normal again here. This will be the refracted ray, and this will be the incident ray for the third medium itself. Then this particular angle will be the refracted ray of this, and then again it is an emergent ray is there. This displacement from this particular ray to this particular ray, this line is called the lateral displacement. Okay, so here we will just have this lateral displacement is KL dash. KL dash is the lateral displacement here. Now from K, draw KL dash perpendicular to MN. MN, this is MN, perpendicular to this MM. We have to draw KL dash. Okay, this one. Okay. Now this perpendicular has been drawn and produced, and this lateral displacement of the ray on passing through the parallel slab KL dash, let angle K and L dash is equal to D. This particular angle is equal to D itself, and deviation of the first reaction then the angle NKL dash is equals to sin D is equals to KLN L dash upon NK, KL dash upon NK, this particular NK. This will be the angle of sine deviation, sine angle deviation. Then LK in KL dash is equals to NK sine D or sine D is equals to first equation. In this particular N dash K cos R1 is equals to N dash upon NK, that will be equal to NK is equals to N dash upon cos R1, that will be equal to T upon R cos R1 itself. Okay, then this T equal to N dash is equal to thickness of the glass slab. From equation number 1 we will get KL dash is equal to T upon cos R1 sin del, or KL dash is equal to T sin I1 minus R1 upon cos R1, which is the second equation, and thus we will be able to get the required expression for the lateral displacement, and obviously, or the shift, or which is obvious portion of the thickness of glass slab. Further, the lateral displacement of shift will increase with the increasing angle of the incident that is I1 itself. So this is how this particular angles are being made, and thus you will be able to understand this particular value, and this is how the expression of the lateral displacement is being taken by me in the board itself, and I explained to you. So let us do the next topic, which is called the critical angle. So I will be explaining you the critical angle, which is the next topic in this session itself. Let's see that one. Let's see this one, critical angle. Critical angle for a pair of a given medium contact can be defined as the angle of incidence in denser medium for which the angle of refraction is rarer medium is 90, and the value of the critical angle depends on the nature of the two medium in contact. So this particular angle is the critical angle in which it is defined by IC itself from the medium number 2 to the medium number 1, that is denser to rarer, not from rarer to denser. Okay, we have a glass slab rarer to denser and then denser to rarer medium, but we are considering here as a denser medium to the rarer medium, for which the incident ray is for which the incident ray IC, there will be an angle 90 degree in the rarer medium itself, and that is what we call the critical angle. Snell's law, mu2 is equal to sin IC is equals to mu1 sin 90 degree. So mu1 upon mu2 is equals to sin IC upon sin 90 degree, that is mu1 upon mu2 is equals to sin IC, where sin 90 degree is equal to 1. So mu2 upon mu1 is equals to 1 upon sin IC is equals to 1 upon 1 mu2 implies that 1 upon is equal to 1 upon sin IC itself. In water, the critical angle is 48.75 and the refractive index is 1.33, and some of the angles are given in this particular notes. I am sending that note to you in a PDF format. The refraction of the light through the rectangular glass slab also I am giving it in your PDF format. Now we will go for this total internal reflection. I will tell you what is total internal reflection now. It is. So let's see that one. Now students, let us see what happens in the total internal reflection. In this way, this is a diagram which I have drawn it for you. In this particular rarer medium is this one and this one is a denser medium. The light rays entering from the denser to the rarer medium, what happens? This is the light ray entering, okay. So this will be the critical angle here, okay, because it is a denser medium, this is a critical angle, this is the angle of refraction here, okay. So this light goes in this direction. When it is a little bit greater than this particular angle, and this will a little bit greater than this angle, okay. And what happens from rarer to denser medium, again it is bending down, okay. And a time has come which is already parallel to the surface itself, okay. It is parallel to the surface. When the light rays comes from here, this is parallel to the surface, and the last thing is there when it comes, it is towards the surface, inside the surface itself, and this where the total internal reflection happens, where the critical angle is less than the incident rays itself. Okay, this is the incident ray here. Okay, sorry, this is the, yes, this is the incident ray here. Okay, I, yes, it is I. Okay, the critical angle is forming here, and thus what happens when a ray of the light travels from denser medium to the rarer medium, it is incident at the interface of the two medium at an angle greater than the critical angle of the two medium. The ray is totally reflected back to the denser medium. This phenomenon is called total internal reflection. So it is totally reflecting back to the same medium itself in this particular manner, and the rays move towards a particular direction, because from here the light rays are coming. So it's natural that it will travel to a long distance. When it is traveling to the surface itself, the critical angle is forming here in this particular ratio, in this particular angle itself, and when the critical angle is forming in the inside the water itself, thus the critical angle is less than in comparison to that of the eye, that is incident ray itself, and thus this water air interface is being given to you, and here the angle, the critical angle is forming. This particular angle is equal to 90, which is defined by D itself. Okay, and we know that the critical angle is what it is. It is the angle of incidence in the denser medium, from which the angle of refraction is in the rarer medium is 90, and this value of critical angle depends on the nature of the two medium in contact with each other. So necessary condition for total internal reflection is a place where the rays incident on the surface of the two medium should travel in a denser medium itself. Okay, it will travel in the denser medium, and the angle of incidence should be greater than the critical angle for the two medium. So angle of incidence will be greater in comparison to that of the critical angle itself. So angle of incidence is greater here. Okay, so it is critical angle is forming here itself. So angle of incidence is more in comparison to that of critical angle here. But in these cases, critical angle is not greater than the angle of incidence was less. Okay, this is angle of incidence. Angle of incidence will be less. So this will be the angle of incidence which is less than, which is greater than critical angle forming over here. So we will move to the next topic. Next topic is mirage, and I will try and tell you how to just go for this particular mirage option or mirage topic by your own, because you know it very well. A shadow of a tree is forming in a inverted manner in the in this desert. What happens? A tree is observed at its place when there is the air above the ground at its uniform temperature. It's okay. So this is just because of the temperature. So just go through this particular mirage, and optical fiber, we will just move through this particular optical fiber. So in this optical fiber, and I will tell you what is happening in the optical fiber topic, and the topics which are there in the after this particular topic is refraction at a spherical surface. This I will tell you how to make the assumptions. Cartesian of sign conversion of spherical lenses, concave and converging lenses, and diverging lenses, ray diagram formation, and leaving this for you. You have to make it by your own, or study by your own. If you have some doubt, you can directly contact me. Okay, and assumptions for the lens maker formula, I will tell that one. Linear magnification produced by lens, I will tell you, and I will give you the mirage topic in PDF format, and optical topic also in PDF format. So let's start the optical topic now. So looking forward, in next video I will teach you the optical fiber. Thank you, students.